So if you saw from we're going to try and explore, not going to try, we will explore exactly what, now that we found out about permeability, we know that permeability behavior and relative permeabilities are intrinsically linked to the capillary pressure versus saturation curves. We can stick them one on top of each other. We have no-go zones in each side corresponding to the irreducible saturations of the wetting and the non-wetting phase, such as kind of on this bottom right-hand figure here. And so we know, first of all, what these chimney things emanate from. They kind of come down from the fact that the saturations in these zones change in the smear zone as it comes through. It's controlled by capillary pressure above the water table. We understand a little bit about that. We understand that they potentially pool when they come to capillary barriers. We understand that if the capillaries are small, then the entry pressures are large, and therefore they act as a capillary barrier. If there are chinks or breaks in that where we can't get through, then those are the zones where we start getting incursion and saturation at zero saturation of the non-wetting fluid, for instance. Because what we're doing is we're not so much interested in individual capillaries anymore, but we're interested in an REV. And so this REV that we have here might be 70% NAPL and 30% water. You can only see the NAPL because we know that the water will be on the grain surfaces and at the grain-to-grain junctions, but nonetheless we know that some kind of architecture inside here is represented by this curve. And so what today is we'll go back a little bit from our understanding of flow behavior, multiphase flow, and really just look at the equilibrium distributions of NAPLs in the subsurface for lighter than water phase liquids and denser than water multiphase liquids, non-aqueous phase liquids. So that's our plan for today. So that's where we're going to go. I guess, so I'm going to jump around a little bit, but not too much. Well, mainly going back to our notes. So if I go back to our notes, this is our plan for today. That's kind of your recap, but probably we might say some more things as well. And we'll talk about how these things move in the subsurface, not in terms of their velocities, but of course their velocities ultimately is of some interest to us. But we'll look at how they take on this mantra of some saturation profile in the subsurface that is driven by the capillary pressure versus saturation curves that we have. We've dealt with this a little bit already, because you remember that this figure that we'll look at now, if I can find it, says lots about our system. I didn't think it was this far. Geez, we've got to get through a lot today. Yeah, this figure here. So we've seen this figure before, and I won't go to into excruciating detail, but to point out the salient points. The salient points are that each of these are our capillary pressure curves turned right way up or upside down. Each of them have capillary pressures changing from zero at the water table by definition, where water pressures have to be atmospheric and in both phases, and increasing in height and increasing in depth because of the way that the wetting fluid and the non-wetting fluid are water and air in this particular case. Air with very low density, and water and DNAPL in this case. And it's just the difference between these two pressure differentials as we go deeper and deeper that increases. And so it's this capillary pressure that defines this. So if we ignore hysteresis and the fact that these capillary pressure curves have a second limb, then we can follow the fact that the form of this says that there's a tension saturated zone, which is water saturated because the air can't break into it. It's 100% water saturated. And above this pressure, air can get in at very low saturations, and as the capillary pressure builds as we go higher up, it becomes more tensile, and the saturation of air increases at the expense, which is the non-wetting fluid, at the expense of the saturation of water. Wetting fluid, non-wetting fluid, etc. And so if we think about what these would look like, it would look like a profile where we have, if you take a portion of the aquifer up here, you'd think that as a result of that, then the relative saturations would kind of be given by this magnitude here. So they would be 30% water, say, and 70% air. So that's exactly what this curve looks like. And so that kind of looks a bit like the chimneys we have, although we've looked at the chimneys in terms of DNAPL, which is a bit different. So let's not go there for the moment. If we look at the converse of that, so this is an air-water system. If we look at the converse of that, which is a DNAPL water system, then the same thing applies. If we go down to this depth here, the capillary pressure is given by this separation here. If we go to this point here, then the capillary pressure is given by this amount here. Clearly they're growing linearly as you go in depth, and they would scale. So capillary pressure would be equal to the elevation multiplied by the density of the non-wetting minus the density of the wetting times gravity. These are unit weights. That's all this is. And again, it just defines a behavior so that as you go further within the subsurface, if we're at this point here, if we're at a depth corresponding to a capillary pressure of whatever, then the saturations in this particular case would be, this would be 100% water, this would be water. And this would be the non-wetting. Again, something like 70-30 in this case, of that order anyway. So you see what's going on. So these give us a picture of what's going on in the subsurface. So I think perhaps we'll just take a kind of a leisurely stroll to try and understand what these systems might look like in profile, rather than just looking at these graphs, and see if they kind of make sense to us in terms of our understanding of these cartoons that we've looked at in the past in terms of smeared traces. So that's our goal for today. So, well, I guess we're in the right one. So I don't want to give you whiplash, but let's look at some pictures and let's pull out of the important things that we need to. So the first important things, I guess, are this. This is the Vadose Zone, which we just drew in the first top left of those figures above the water table. And so the ordinates are exactly the same as they were before. This would be the water table, which was at atmospheric pressure. As you go up in here, you go in terms of different components. You'll remember the terminologies for these. I'm not sure I can draw it all that well. Pendular zone, by definition, was if we had grains in contact, then first of all, there'd be kind of a monomolecular layer of water on each of the grains, but also the pendant stuff would be this torus, which existed at the joining of the grains, like a donut, a torus that went around it. And so that would be what we referred to as the pendular zone. Pendular zone, a pendant of water, if you like, held there. And the funicular zone would be where, again, for the same geometry, whoops, I didn't mean that. If you had grains that exist, then a bubble of air. So everything around here is water except for that bubble of air. So this, if I can try that, this is blue is water. And funicular means like a cog railway, funicular railway. It means that to move this bubble, you have to carry it with the motion of the water. And so they represent fundamentally different components. And so that on average, if you look at the saturations of this REV, so the REV would be the volume that includes enough grains that it's representative of the rest of the aquifer. The representative elemental volume, REV, is that each one of these would correspond to whatever is in there. And so the tension saturated zone, almost 100% saturated with water, very little air, perhaps a tiny amount of air left in it because of what we understand about irreducible saturations of air. This would be the minimum amount of water you could have in the system. I guess this would be SW0, irreducible saturation of water. This saturation would be 0 here. And this, I suppose, if you drew it on this would be the irreducible saturation of the non-wetting, NW0. And this here would be 100%. I'm beginning to get frightened by this. I think I might have not had a shower today. Everyone's moving away from me. Need power? But you're supposed to be just taking notes. You're not supposed to be doing your homework.
I mean, including notes. I take notes on my document.
Fine. I make no judgment. So this is completely a free-ranging class. So anyway, so that's what these capillary pressure versus saturation. Yeah, I know you need your computer to take notes as well. So, and the interesting thing is, the other notes here go to make the point that this capillary fringe is high when it's very small pore spaces. So silts have very high capillary fringes, gravels and sands much less, because what we know about the size of the capillaries, we know something like, the most simple of equations are something like this. That the capillary diameter, interfacial tension of water, which doesn't change very much, unit weight of water, which doesn't change very much. If you change the diameter of the pore space, if you decrease it, then this goes up. And so these increase as you get smaller diameter pores. And smaller diameter pores typically exist when you have smaller diameter particles. They go one in one, as you can imagine from just looking at the packing of particles in some architecture. There'll always be smaller pore spaces if you have smaller particles. So we'll talk about the Vadose zone for a little while. Obviously this is the Vadose zone with water and air only, nothing else placed within it. But what about if we dump some gasoline in the top of it? Then these figures follow on directly from that. And so these represent the same boundaries as before. They're defined in terms of content. So you'll remember that we defined saturation is equal to the volume of fluid alpha divided by the volume of the void space. The volumetric moisture content is defined as the volume of fluid alpha divided by the total volume. And so since porosity is given as the volume of voids divided by the total volume, these are just definitions we've already seen, then the upper bound for this is just the way that agronomists define saturation by volumetric moisture content. So by definition, when all the pore space is filled, this would be a saturation here of 100%. And corresponding in this particular case would be a volumetric moisture content of, I don't know, 0.2, 0.3, I guess it's 0.38. So you can be bilingual in speaking between petroleum engineers, some extent, some groundwater hydrologists, and some groundwater hydrologists use volumetric moisture content. But same scale, it's linearly the same. 0, 100%, and vary between. And so this is the same deal. This is the irreducible saturation of the non-wetting fluid, which is air in this particular case. So this would be the amount of air that's in it. This is the water saturation originally. Which is, I don't know, looks like the saturation is 90% and 10%, but if you do it in terms of these volumetric moisture contents, it's, I don't know, 0.04, and whatever the remainder is. I won't quote the numbers because it's not so obvious. And so this is what happens. This is your pristine condition. So I think we're going from, we're going down here. So you introduced a spill. This is gasoline in the top. All of a sudden, you've introduced it on top of here. So now you change your saturation. So if you went across a section of this, then you'd see different components. I guess you would see air. Certainly you can figure this out. This is the volumetric moisture content of air. This would be, am I going to run out of colors? This is magenta for oil. And this would be water. See if I can remember my color scheme as we go through. H2O. Not just H2O, but it's liquid water. So. And so that's what these happen. So you see this little tongue that's advancing here of the oil as it pushes down. So this is after 2 minutes. No, 2 hours, not 2 minutes. And so it's quite fast, right? On the scale of some kind of project. If something's happening quickly in 2 hours, it's going a reasonable distance as well. You know, this is about 1.5 feet, 60 centimeters is of that order. So this is not a trivial scale. It's not a laboratory sample. It's certainly an experiment in the laboratory, in a column with just soil in it and in a graduated cylinder, but it's happening relatively quickly. After 8 hours, a third of a day, then this has changed so that now the oil, if you took a section across here, it would be, this would be the oil, this would be the air, and this would be the water, liquid water. And you get those amounts from it. Oil. And so you see that if you looked at the proportions, I'll talk in terms of saturations. This is 80% saturated, I'd say. This is 15% of that order, and this is 5%. Just ballpark numbers in terms of relative proportion. And so that if you take a single REV, it would include each of those proportions in different parts of that around the grains in there, but it would be within those proportions. If you went to an REV next to it, they'd be in roughly the same proportions. If you went down further in the system, then they would obviously change. So that if you went down here, you'd be 80% water, and you'd be 20% air in the system, and no oil, because it's only got this far. It stops there because it's lighter than water. You'll notice that it's kind of compressed the water table. So now the water table looks like it's at 31 centimeters, whereas before it was around the same, I guess. 31 centimeters before was around here, but it's changed kind of the morphology of this by allowing this plug of fluid to move down. And if you allow time to carry on, I don't know what the final conditions is, but it's, I guess, more than 8 hours, then what happens is that this part here, more stuff just accumulates from the top and drops down in the system. This extra supply does two things, I suppose. You can see that this band here is now less. So some of this stuff from here is drained down, and it's become a thinner band in terms of saturation. And obviously the stuff from here has ended up accumulating not on a capillary barrier, but on a pillow. It's buoyed up by the stuff underneath it. So it's trying to compress the fluids in the tension saturated zone by sitting on it, just like sitting on the top of a swimming pool. And so now, I suppose, if you chose an opportune location to draw a line through, then you directly see what those proportions are. So this would be air. This intercept here and here, right? This would be water. Sorry, this would be oil, not oil. And this would be water. And so you see that it's gone on this point here. Maybe it's 80% oil, maybe it's 7.5% water and 7.5%, well, I guess it'd be 10% of each roughly, slightly more air. And so if you think about what that would look like if you drew a cartoon of it in the subsurface, I suppose it would look something like this, right? This is our chimney. I guess I should have drawn it aligned with it. This is our chimney, which is this portion here. It looks like it's at 10% saturation. Pretty close to the irreducible saturation of the non-wetting fluid. You probably can't get much less than that once you've smeared it with this stuff. The bottom is where it accumulates. It accumulates because it's buoyed up by the water underneath it. It's a relatively high saturation in here. I don't know. What did we say? 80% saturation. It's an LNAPL by definition. Because it's sitting on top of the water table. Otherwise, there'd be no reason for it to stop there. It would just keep on going if it was denser than water. Just like salad dressing analogy that we used earlier. And what else? I guess it's interesting to note that this water table, which was here, which was at 31 centimeters before, kind of about the same place here, so it didn't move, now looks like it's lower. It certainly is lower, right? It's now of the order of 20, or perhaps a bit higher, but you see that it's moved. So it's been compressed down. And so the original water table would have had a tension saturated zone above it. This is what we'd call the capillary fringe. Or the tension saturated zone. This is the top of the capillary fringe. The capillary fringe would be the area. Fringe is an area. And that would be the top of it. And so it starts looking like the systems we looked at. And so we can understand this all in terms of these capillary pressure versus saturation curves. And of course, this curve here looks like a capillary pressure versus saturation curve, right? Increasing capillary pressure, changing saturation in terms of written as a water content, but equivalent to a saturation if you just do the change in units, change in the multiplier. Okay, so that's what we'd expect to go on. So what happens to the, I won't go explaining it, that's done there. So what happens if we now, I think this was in the lab, I'm almost certain that this was in the lab. And so you'd take a long, tall, graduated cylinder, 4 inches diameter, pack it with soil, dump some stuff in the top, make sure that there's a place for the water to get out to the bottom to keep to allow that to occur, and then just allow it to compress this, and measure the relative saturations with elevation maybe by recovering by architecturally excavating the column and removing the material and looking at sampling it to see how much fluid you have in what proportions in each of the parts. The other way you can do this is you could do it in situ, and I think this is in situ, but I'm not sure. Can't remember, it doesn't matter. But it's representing a real system, and the system is essentially the one as before. So, but now I think we scoop from first to second to third to fourth. And so the idea is that this is the system when it exists previously. This is the gauge pressure. So I can make them larger perhaps. So this is the pressure within the system. So although we perhaps don't know exactly how to do it, by definition, if we look for the place where the water pressure is atmospheric, then where we find that location by definition is the water table, just by definition. It's not labeled in any other way in the fact that by definition the water table is at atmospheric pressure. There's a zone above it which is tension saturated, which is this region that we talked about here. And it's tension saturated because a bubble of air can't move into it because the pore space is too small. But if we could measure the pressures below that, then we'd find out that the pressure here was equal to what? P equals gamma W Z, perhaps H, right? We can use this expression because we know that the ordinate is equal to 0 here. So this is just going down inside a swimming pool. It's always the same as going inside a swimming pool. It's not changed in any way by the fact that the porous media is there. All that matters is that the fluid here is connected to the fluid here in some path that you can get to. So they are connected. And by extrapolation for this, as we go within the Vadose zone, then we can just extrapolate directly above this. And so as we go back here, we're basically pulling the water up. And so this pressure here is equal to minus unit weight of water times H, call it H sub C. That's this. It's negative, so it's in tension. So the water pressure is in tension. The capillary pressure is given by pressure in the non-wetting minus the pressure in the wetting. This pressure in the wetting is in tension, so a minus minus a minus, this is essentially 0, is a positive. So this would be a positive capillary pressure, but it's defined in gauge pressure in centimeters, actually it's defined by a height. So this is in centimeters. So you know there's an equivalent between, so this would be the height of a column of water, would be what these are. So I think I'm over-explaining it. But the point is, when you take this is what the pressures within below the water table and in the Vadose zone in the capillary fringe. There's no reason that this should change trajectory once you get above the capillary fringe. You're just holding up a connected volume of water between this point and that. It has a slight divergence, but not very much. You dump in oil at the top. It flows down, and so what it does is it takes it makes itself a new oil table. So I guess this we can describe as being two things. An oil table and a water table. Interesting terminology for table. And all it means is that, by definition, a water table is where the pressure is atmospheric. This dotted line, as you come down here, is where the pressure is atmospheric. It's atmospheric at two places. It's atmospheric at the location between the saturated groundwater zone below and kind of a tension saturated zone above it, which has been pushed down by this supernatant oil as it's coming down. And that where the oil pressure, if you extrapolate it to this point, is also equal to 0, then by definition, since a table is where the pressure is 0, this represents the oil table. And so you'd think that the saturation here might be quite high of oil that sits above it, in the same way that it was when we thought about it here. We're mimicking the same case. So time 1, time 2, time 3, you get the same thing developing. This is 3 and this is 4. This now, if we mark the individual tables, this is a table which is the top of the supernatant oil. This is a table which is the top of the water. They're separated by some. The saturated groundwater zone goes from atmospheric with the pressure gradient, which is going to be the same as due to a column of water. So this dP, dz dP is just equal to just as we've seen before, just like in a swimming pool, happens to have had its ordinate changed by this dotted line is the same in all figures, I think, at 81. And this has come up slightly to be able to do that. So it's defining the same kind of behavior that in this zone here, if I draw it here to here, this is oil. And I guess I was using red for water before, so I'll keep with that. And below this zone here, this is water. And there may be compressed air here, or it may be that this oil is completely, probably this oil has completely squeezed that out. So my guess is that this would also be oil in this zone here. So you've got oil sitting directly on top of water. You've got the Vadose zone above that. You could guess what the saturations would be in here. And if you think about this kind of profile, air, oil, lighter than water, and water, it's not really very different from this very last figure we looked at here, which is you go down through this, you go from air to water to oil. So it's just translating these figures into something that hopefully means something to you. And so we're saying the same thing. In one case, we're measuring saturations as a function of depth, and they look like this. In the other case, we're measuring pressures as a function of depth. So instead of being volumetric moisture contents, these are pressures. But we know because of the pressure capillary pressure versus saturation curves that pressures are kind of uniquely related to saturations. And that's why it's just a different picture of the same thing. And so if we looked at what that was like on this left-hand side, then I suppose what we're doing is we're drawing a section through here. So this is mainly air. You can imagine there'd be a smear of something in there. This would be the oil that starts here. The oil depresses the water table a bit by its self-weight. It's certainly less dense than water, but if you have a big column of it, then the weight of that is actually quite high, pushing it down. So it slightly depresses the water table here. And so the oil zone would exist in this cross-hatched region here, including this. So this would be oil. And then this would be water below it. And I guess I've drawn water as red. So the groundwater saturated zone would do this. It would be an interface here. And herein lies the interest in that the contact between the oil and the water across this interface this is a dissolved plume. And you see immediately that the water table has some very slight gradient to it. dH or dpdx. And we know that the flow is equal to permeability, viscosity of water, dpdx. We've done this ad nauseum. So you know that there's groundwater flow in here that's moving at some velocity. We can calculate the Darcy velocity, which is really what this Q is, right? This is the Darcy velocity. And so if we know the Darcy velocity, we can calculate the advective velocity, which is equal to the Darcy velocity divided by porosity. And so we could do all kinds of weird and wonderful things to say that velocity is equal to length over time. So in other words, the length traveled in a given time is just going to be the product of velocity and time equals length. This is length, not lambda. And this would be the advective velocity. So you've already done something like this. So you can do something useful already. If it happened to be, if for some reason portion of this groundwater only zone was partly filled with NAPL, then we'd perhaps have to use a relative permeability in this to be able to represent that. That should be easy enough for us to do as well. So that's maybe what we need to know about gasoline escaping from underground storage tanks and what it might look like in the subsurface. And of course this says something about the architecture. So the other thing that we might be curious about, I'm not going to talk about these because we'll do that in due course, is the ramifications of this particular behavior that we talked about here. The fact that potentially we have oil kind of trying to compress the Vadose zone, succeeding in compressing the Vadose zone here. In the outlier portion at the periphery, there's the Vadose zone still exists, so there's air and water in this white region here, saturated in the dark region below the water table, mainly oil only in the magenta region above it. And that's kind of a consequence of what we see here, the oil table not quite having squeezed out all of the Vadose zone. So the question comes, if we put a borehole down, and I guess I can do this, if we put a borehole down through this, and that borehole went down from the surface, not like that, oh, I guess it finally worked out. So you're standing on the surface here, and you don't know what it is. So you're standing here, and you're wondering what's underneath your feet. So one way to do it would be probably not drive a borehole through the barrel, but drive a borehole down. It would allow the fluids to flow into here from the area around it. And you'd like to be able to use that to be able to say something about maybe where this interface was, where this interface was here, and you need to understand something about what's going on with these water tables to be able to understand the distribution. And so we can certainly do that. So let's take a break, and I have a couple of movies here somewhere, I think, that I opened. So what you might want to do, if we look at, I don't think my, where's the video?
What I have here is a water level meter.
It does work.
What that does is it reads the depth of the top of the groundwater surface. When this tip today we're at an agricultural well site, and we're going to measure the static water level in this ag well. What I have here is a water level meter, and what that does is it reads the depth of the top of the groundwater surface. When this tip reaches the groundwater surface, it completes the circuit, and you'll hear a beep like this. I'm going to take this sounder and lower it into the well.
Yeah. Presume those things are just weights to keep it going down if you have to go down a deep hole. So a two conductor wire.
The sounder is hit the top of the groundwater surface.
So two conductor wire with a length scale on the part between it. The two conductor wires are separated down the borehole. Once they hit water, you make a circuit, light goes on, and that's the depth of water. You know, not super sophisticated, but something very simple that does the job. And so you can presumably measure the depth to the water table. We made the case that we're interested in being able. How big
This is
is
a
it?
short description of the NAPL flute system developed by flexible liner underground technologies. The NAPL flute system was developed to detect pure product LNAPLs and DNAPLs above and below the water table in soils and rock. The NAPL flute system is a simple and cost-effective technique for mapping NAPLs. We have developed a color reactive cover for detection of pure product. In one application, a compressed NAPL flute liner is inserted into push rods.
So this is, I'll let it go so you can see a clear picture of it. So
This is injected into the liner as the rods are pulled.
sometimes called direct push technology. So the idea is that it comes on a tractor, it just pushes rods into the ground. These rods have a conical tip on the tip, and so that it makes basically a borehole that is kept open by the rods, which are the borehole wall, and allows you to then advance things down to the bottom of it, such as these piezometers that measure either pressure, but also have, in this particular case, some kind of skin on them, which is reactive to whatever fluids it comes in contact with. And so you push it down to the bottom as it goes down with this instrument, and then these the sheathing reacts differentially to whatever is present in the subsurface.
Causing the liner to dilate against the whole wall. If there,
So you have a central tube. That central tube has this sheath of fabric on it as a sleeve. It gets pushed down to the bottom of the hole, and then once you're in the bottom of the hole, you have the sacrificial tip on the probe, which gets left there like a barb on an arrow, and then you pull the rest of the tube up through the hole, and you leave a string that has a central piezometer, a tube maybe an inch in diameter that can measure the pressure and sample fluids from that depth. And then around that, it also has this this fabric
pure
that's
product
present.
it will make a stain on the color reactive liner. When the liner is inverted out of the hole, here it is, and laid out on the ground, you will be able to map the exact location and depth of the contamination of the tape measure. Here are the 5 simple steps for installing an
This one.
NAPL flute color reactive liner using the direct push method. Step 1, push the rods to depth. Step 2, install the NAPL flute liner and fill the annulus with water. This liner is going down very easily. Once the liner is in the rod, water is added to the annulus. We do this to keep the liner from dilating in the rod before the first rod section is pulled. Step 3, raise the rods one section and inject the water to dilate the liner in the hole. That's good. Just hold the tube now. Injecting to fill the liner. Step 4.
Keep on
Inject
going.
the water and then raise the rods. Repeat step 4 until all of the rods are removed. Injecting to fill the liner. Step 5. Pull the tube to invert the liner from the hole. By inverting the liner out of the hole, we keep the color reactive material from touching any other section of the hole wall.
I guess you turn it inside out. So, Manchester, England, I didn't realize that. Anyway, so you get the idea. The point is that you can use this, you'd like to be able to determine exactly what these distributions are with depth. It's not altogether obvious how we might do that, but certainly seeing what we've talked about now, you can do it in 2 ways. You could drill a hole and you can drop a depth sounder into that, which makes contact, and you can get them that can pick up an oil interface and a water interface which have different resistivities. You could use something like this liner. You can use a stick or a ruler which has paste on it, which is also able to be pushed down into an open borehole and then defines exactly what the different components you have at different depths. But the important point is that if we know exactly what the height of these levels are we able to project from what we see in the borehole as to what we have outside that borehole? I suppose one question you could ask yourself is, would they be the same? Is the thickness of stuff floating in the well exactly the thickness that you'd expect to see in the aquifer? And the answer is kind of no. And so this is the idea here. And so we want to be able to simply correct for that. And it really revolves around the fact that within the subsurface, as we've seen, we have an oil table. So now our green stuff is our oil, blue stuff is our water. So we have an oil table that exists on top of a water table. This would be the compressed capillary fringe between them. This is the borehole that goes through them, which has very low capillary resistance. It's a big hole, big borehole, so it can get as much free product in there as it wants. Got an itchy nose here. And so what we can do is we can do a simple force balance to see what a height that we measure in the borehole means in terms of what we have in the subsurface. And it's really a relatively straightforward calculation. We know that we have a water table. We know that the water table, by definition, has to be zero pressure at this particular point, atmospheric pressure. We know that the oil table has to be zero atmospheric pressure at this point. We know that this has to be zero pressure at the top of this as well. And so we can use that to understand exactly what the pressure must be within the borehole, the water pushing upwards, and the gasoline pushing downwards at this interface. And so the basic idea is just this. We know that the pressure here is atmospheric. It happens to be atmospheric here as well, but we don't care about that. I'll use a better color. And so merely we know that the water pressure here is atmospheric. The water pressure at this point here if we do it off to the side, would be just this, right? P, Z. So immediately we can get the pressure at this point here. It's going to be equal to the density of water, the height of that water, which we're calling W, multiplied by gravity. So we have that pressure acting upwards in the borehole. In the borehole acting downwards, we have a column of supernatant oil. And so the pressure at this point on the other side acting downwards is going to be the height of this oil times its density times gravity. Just T gamma oil. And what we like to know, I think, is we would like to know the value of this height here. We'd like to know this, and of course this value is T minus W. So T is the depth of this interface, W is the height of this interface, ignoring this Vadose zone. So T minus W gives us this green zone here. So if we can equate these have to be the same. By definition, right? Pressure acting upwards because it's at equilibrium. That gives us this expression here. If we arrange that in terms of W, we get W as a function of T. And then I suppose, by definition, to get T minus W, is equal to T 1 minus rho 0 over rho W. So oil is always less dense than water, so this is always a fraction, less than 1. This is always less than 1, and so the height of the free product, this T minus W, is always going to be less than the depth we measure, right? That's the take-home message. So you go into your borehole, you measure the thickness of the free product is T, then the amount of stuff you have in your aquifer has to be less than it by this fraction, that's all. And so that allows you then to rationalize what we've done before to be able to figure out exactly how much might be present within the column. And so that's a pretty simple calculation. Well, I mean, you could do it just by looking at it, right, in terms of this. Yeah. What's the best way to explain it? Well, you know this. It would look something like this. This would be our profile. So this would be the water table at the bottom. This would be as far as it goes up. So this, I guess, would be T minus W. So this is in the aquifer. You know that we're limited because some of this is going to be water at SW0. So this is going to be 10% water, right? You can't get out of it. 10% or something of that order. And so if you want to calculate how much is present within the column, then the height of this column multiplied by its cross-sectional area. So if you draw it out in plan view, this is your lens that's sitting on top of your water table. It's of some area A. See if I can draw this as perspective. This is A, this is T minus W. So this is the volume of the aquifer times porosity is the volume of the pore space. These all included, right? This is the porosity. So this is the volume of the pore space. And so if you take that volume, and it's done up here somewhere, I'm getting them both the same. Thickness is this. This is the volume of the aquifer. This is the void volume of the aquifer if you combine them together. The amount of water that's present within the system is left there, so that's taking up volume that otherwise would be free product. And so 1 minus the saturation of water would be this length here, which would be oil. And so if you multiply the volume of the pore space times the effective saturation of oil that's in the system, then you get the amount of oils in the system. It has some little bits on the bottom where you'd have this, but they perhaps cancel out for each other, so we don't perhaps have to worry about them too much. And I suppose if we wanted to suck all of the oil out of the system, we'd be able to get it out, except we wouldn't be able to get out the irreducible saturation of the non-wetting fluid. So the saturation of the non-wetting fluid, irreducible, would be stuff that we wouldn't be able to get out. And so you could imagine that this term here is not just 1 minus SW0, but is actually 1 minus SW0 minus SNW0. Times, just for completeness, times area times T minus W times porosity. So, same equation. So in other words, just add this equation in here. So this is everything except for this amount is what's in place. You have to subtract this amount because when you pull it out, you can't get it out. And so that's the reason for adding the extra. So just becomes a volume gain. I guess that's what's written down here. Okay, so you're able to figure out exactly what's recoverable. I'm going too slow again. So if you remember, so these things start looking like the capillary pressure versus saturation curves. You might remember that we took the capillary pressure saturation curves, and we'll revisit this. And so we had capillary pressure versus saturation, and the curves looked like this. And we transformed it to something that we called Brooks-Corey, which was log capillary pressure versus log effective saturation. And it turns out that this curve here transforms to a straight line. And we didn't give any reason for why we wanted to do that transformation. These curves are exactly the same, they just transform because one's on log-log space, one's on natural space, and they're transformed. But if you think that the saturation profile that you have in place can be given by the capillary pressure versus saturation curves as you go down, then you could also write the saturation versus capillary pressure curve in this linear form. And if you do that, you can come up with some very complicated expressions that give you this behavior. And I'm not going to go through them. It's in Fetter if you happen to know own Fetter, and pages of equations which don't really matter, but it matters that you understand that what we just did is essentially the same thing. You end up with this zone where you have, this is also out of Fetter, you have a zone which is oil in the subsurface. It's capped off by this little portion at the bottom, so it's no different from what we drew here. This picture is just this in microcosm. This is mainly oil, not mainly, this is only oil. This is water. And you can calculate what these volumes are using the method we already just said a page before, or you can use the real capillary pressure versus saturation curves to get very complicated expressions that describe this exactly, but it won't improve your estimate that much. And so we're just working on the assumption that this would be the profile of the oil as you go on the subsurface. This is water, which you can't remove, and the irreducible saturation of oil that you won't be able to recover from it is also given by this amount on the left-hand side. Identical to kind of what we drew here, and the same rationale. And a much simpler and straightforward and usable expression to be able to evaluate those. Because we know that the values of these irreducible saturations are 10 or 15%, right? Each of them. So immediately you have some values to do for this. If you have, so if you know what the thickness of free product is, if you know what the relative densities of the liquids are that are present, you know what T minus W is. If you know these are 15% and 15%, and you know your porosity is 30%, immediately you have an estimate of how much stuff you have in place in a calculation that you can do in about half a minute. So, I'm lagging terribly behind in terms of time, but the stuff that we have to talk about is perhaps pretty straightforward. So we talked about the distribution of components in the subsurface. So this would be exactly the same as we've done before for gasoline, just shown in a slightly different way. So in the top part, it's mainly air saturated. There's a chimney of smear, if you like, of gasoline, and that gasoline sits on top of water, which is the dark gray portion here. And so this is buoyed up, of course, by the water table. And if you assume that the water table doesn't move, then it just stays there forever. If during summertime and wintertime the water table migrates, you can imagine that this shelf that the free product is floating on drops. As it drops, it will provide a smear. The smear will be on the full width of this lens that's sitting on top of the water table. So as it goes down, the smear goes down from this whole portion. And it will leave that there. And then in the wintertime, when recharge occurs, the profile, of course, would be to have the oil sitting. This would be an oil lens that's sitting on top, right? This is the kind of high saturation of oil sits here, which is this lens, with water underneath it, which is the black. And then when the process is reversed, then it shoots this buoyant layer up here as the water table rises. It plows it up as a snow plow in front of it, and you left this residual. So now if you look down through the section, you have oil at residual saturations that originally came down as a chimney. The big mass that is at saturations larger than the irreducible saturation of oil has been pushed up back through it. And so this kind of portion here has retreated, but you're left still with this reverse chimney. So you have a chimney here in the Vadose Zone, which you originally had at the top here. But now you kind of have I suppose you could think about it as an inverted chimney below the water table, which is due just to this process. Pretty straightforward. So that's all really I want to say about LNAPLs. DNAPLs are the same, and maybe perhaps we look at these two figures and talk about the ramifications. So three more points. One is that in the same way as we looked at the behavior of LNAPLs, we could look at the behavior of DNAPLs. But we know that DNAPLs, denser than water, aren't buoyed up by the presence of the water table. And so anything that shoots down onto the water table will just keep on going. And so if you think about drilling a well bore in it, then the height of the DNAPL that will appear in that is given by some upper boundary. If you drilled a deeper well, then because it's kept on going, then it will fill up to the same height, but it will give an apparent thickness which is much deeper because your well just happens to be deeper. And so this profile of what the saturation with depth would look like is given in terms of our capillary pressure curve that we just said. That it would be mainly air at the Vadose Zone, a portion which is water, and then below this would be DNAPL. We know that when it's introduced to the surface, it's going to shoot right down to the bottom because it's denser than water. And so it will preferentially gather at the bottom. And so if you look at the components, this will be DNAPL. Physically, it would be a big thick lens on the bottom, which is stopped by some capillary barrier, nothing else. Above that, it would be water. It's going down here. And the slope of this curve is controlled by the gradient of the capillary pressure versus saturation curve. So you could imagine, I think it occurs in the figure below. So you can imagine that this is a capillary pressure curve, and if we drew it, if we flipped it, it would be exactly as we're used to seeing them, that it looks a bit like I'll get to GIU soon enough. So you can imagine a curve that looks like this, or a second curve that looks like this. So in other words, this, I'm just flipping around this axis here. Over. And so we have two curves. So this curve would be a low entry pressure curve. This would be a high entry pressure curve. So if it goes in very easily, then this would be open graded. This would be big pores, large diameter, and this would be tiny pores, small diameter. And the net impacts of this are that for this particular curve, you would end up getting the non-aqueous phase liquid pushing into the water at a very low entry pressure. And so it would saturate to a relatively large NAPL volume with at a relatively shallow depth. This one, you would have water existing down to a very, no, so, yeah, water existing down to very deep depth, and only below this would be the non-wetting fluid, and this would be saturation of water. So initially 100% water saturated, so the left-hand side of this is water. This means that as soon as you get a very small entry pressure, you immediately invade it with NAPL at some relatively high concentration, and therefore, as a result of this, you'd expect to get this distribution that you have to go to very, you have a very thick band of NAPL in this particular case here, because this is corresponding to this portion here. So at this particular height, you have saturation of the non-wetting, which gives you NAPL all the way on downwards. Whereas in this particular case, the amount of NAPL you have in your system for the other condition is only this amount here, which means that at this depth, you're probably still water. So high porosity allows it in very easily, so your NAPL saturation's very easily and high up in the contrast. In this one, you tend to keep water, and the NAPL's restricted to a much narrower band at greater depths. And you can rationalize that based on the capillary pressure versus saturation curves. And so that allows us to be able to link the two together. And I guess the only final passing note is to make the case that was probably already apparent in this figure. If you have a borehole that goes to the center of the earth, then it's going to tell you that your thickness is infinite, right? Because this upper surface is defined by the capillary pressure versus saturation curve and is always the same. And so if you keep on drilling this deeper and deeper, it would erroneously tell you that NAPL has gone much deeper, where it might be actually staunched by a capillary barrier, which you don't know would exist at some higher depth. And so, different from the case of LNAPLs, where you get a depth in the borehole which also seems deeper than the true thickness in the aquifer is. In these cases also, you end up with a thickness apparent within the borehole which could actually be much larger than what is present, because you don't know anything about where the capillary barriers might be placed within the subsurface that would stop that fluid from going down. And I think that's all I really wanted to say in this. Other than, we've talked about porous media so far, in which case we've talked about this layered architecture with a chimney that joins it. The problem is made much more difficult if you have fractured media, where the fluid will only travel within the individual fractures themselves, and therefore, one, it enters into the fractures very easily and can travel long distances laterally and vertically, and also the heterogeneity of these kinds of systems are much more difficult to characterize than a homogeneous, relatively homogeneous porous medium. And so fractured systems are the bane of these kinds of studies, because they just are more difficult to characterize and define the behavior, only because we can't see what is there so easily. But the same rules in terms of capillary pressure versus saturation diagrams that control this response also hold for those systems as well. So I guess in our part in looking at the equilibrium saturations of things, the only thing we have left to talk about is this last one, 2.7, before we start talking about transport, is how we describe the Vadose zone in a bit more detail. And then after that, the material we'll talk about is going to be talking about dissolved components which get carried downstream, which of course are epitomized by this one figure that we had today, which are that in the contact region, well, actually this will do just fine as well. In the contact region, where you have fluid sitting at some kind of saturation in here. So what do we think the saturations might be here of the water and the NAPL? Well, if it's a residual NAPL, then the saturation of the non-wetting phase might be 10%. the saturation of water might be 90%. And so if you wanted to calculate the rates at which dissolved components would be carried downstream as we move from this, immediately we can do that, because we know how to calculate fluxes as a function of relative permeabilities, viscosities, and pressure gradients, which is Darcy velocity. And if we know Darcy velocity, we also know that advective velocity is equal to Darcy velocity over porosity. And so if we have a smeared region in here, clearly it won't be 100% water filled, because there'll be some smeared residual NAPL, but we can still calculate what the velocity of the flowing fluid driven by pressure gradients in the liquid water would be. And if we can figure out what that is, we can immediately get the Darcy velocity, and we can start calculating how long it takes to go a kilometer, and at what kinds of depletion rates of the mass that's present in here might occur as well. So we will do that next week, but on Thursday we'll talk about the Vadose zone and how that behaves first. Okay?